Thank you. Microphone on. Okay, folks. You don't have to write this down, but this is going to be helpful for you to understand what the heck we're doing today, okay? So there will be a piece that you learned today, and by the way, this is the last time I tell you this is how you take a derivative, okay? So you've learned all the derivative rules that you would ever need to know, except for just one last piece. It's not even a derivative rule, it's just kind of what do we do in this situation, okay? Which is kind of cool. So you're going to continue to take derivatives for the rest of your calculus career, where you take calculus 1, 2, 3, whatever. But there's something I need to teach you today, and nobody ends up really struggling with today's lesson. People get it, but only about half the people understand why it works the way that it does, okay? And so I just need to bring you historically a little bit to notation. These two things mean the same thing. This means derivative, this means derivative. This means derivative of a function, and it names the variable x, and we call function y. This is the derivative of y with respect to x. So I'm going to try to just help you understand the difference between these two. So Newton and Leibniz, they were like the fathers of modern calculus, and they used a little bit different notation. So I'll show you what the heck I'm talking about. Suppose I write y is, you don't have to write this down, just follow along. Y is equal to 3, we're going to go 4x minus 1. Okay, everybody good with that? Okay. What is y prime? 4. Got it? Now, just so you kind of understand again what the heck is going on, what's interesting about that is we always focus on this part, right? And you say 4x. Well, why didn't we take the derivative of y and just write 1? Do you know what I mean? Do you know what I mean? Like we didn't do that at all. And so watch, and I'll show you so you can kind of see it. If I write it like this, so I'm going to multiply this equation through by 2, and I get 2y is equal to 8x minus 2, okay? All right? So what we do is we say the derivative of 2y is 2, and we attach a y prime. So we say the derivative of y is 1, and we attach a y prime. So like here, we say the derivative of 2y is 2, and we attach a y prime. And then what's the derivative of 8x minus 2? 8. And so you get 2y prime is equal to 8, so y prime is equal to 4. We come up with the same thing, don't we? You're like, well, why are we doing that? Like, what does that even mean? And note that, you know, f prime of x is the same as y prime, and that's the same as dy over dx. And here's the kind of the best explanation I can give to you. Okay, this is the best explanation I can give to you. When you take a derivative, x squared plus, 3x cubed minus x is say equal to y, whatever. And when you take the derivative of x squared, what happens to the power? It always reduces 1, right? Like it's almost like there's an x here that just kind of like, like kind of vanishes out. It just becomes, this 2x. It's like, well, what happened to the x, right? And then you take the derivative here, and you get, 9x squared, and it's like there's this x that just kind of just vanished out of there, just reduced, right? So here's how Leibniz tried to kind of understand that, okay? He said that if you take the derivative of something, okay, with respect to x, here's what he said. The derivative of x squared, what's the derivative of x squared? 2x. And so what he said is, that kind of mysterious x kind of just floats on over to here. And you get dx over dx 2x. Well, what's dx over dx? That's just, so you just always write 2x. But what if I do this? The derivative of y squared. So if you were to describe the derivative of y squared, what would you say? You call it 2y, right? And then he said, well, there's like this y that kind of floats on out. And so it attaches here. So we don't say that the derivative of y squared is just 2y. We say it's 2y dy over dx, or in other words, y prime times 2y. The idea is every time you take a derivative with respect to y, you attach a y prime. Now, you're probably about a third of with me on that. Trust me, by the time we kind of lay out the notes, that'll help you understand it a lot better. So let's go to your examples here. We're going to talk about something today called implicit differentiation. And in order to understand that and this whole like y prime thing, we need to start with explicit and implicit equations. So here's an explicit equation. Y equals x squared plus 1. Here's an example of an implicit equation. xy is equal to 4. Here's an example of an explicit. Y is equal to sine of x. Here's another example of an implicit. X equals sine of xy. And I'm going to do one more example of an explicit equation. Y is equal to the square root of x squared minus x. And an implicit equation I'll write as x plus y over y is equal to 4xy. I want you to look at examples of each. And I want you to turn and parent share for just 20 seconds. See if you can tell your partner what do you think is the difference between explicit and implicit. Ready, set, go. Okay, what do you got? Somebody give me anything. What makes something explicit? It's solved directly for a variable. Exactly. You can see in all these situations it's y equals. And does a y pop up on the right-hand side at all? No, it doesn't. And that's what we're used to finding the derivative of. In these situations, you notice that x and y are kind of commingled. I mean, they're on both sides. They're not explicitly solved for. Okay? All of these terms mean derivatives. And in order to find derivatives of implicit equations, we're going to use this operation. We're going to take the derivative with respect to x. And we're going to start by using a circle because everybody here can connect with a circle. You remember what they look like. X squared plus y squared is 36. Anybody remember what the radius is? It's 6, okay? And so this is not a function, isn't it? Because it doesn't pass the vertical line test. So far, we've only taken derivatives of functions. What about when you don't have a function? This is an implicit equation. Let us take the derivative. Instead of using f prime notation or y prime, I'm going to use d over dx, and I'll show you what it looks like. The derivative of the following function. So what we will do is we will take the derivative with respect to x of x squared plus the derivative with respect to x of y squared. That's equal to the derivative with respect to x of 36. So, looks complicated. We're going to make it super easy. What did you say was the derivative of x squared? 2x. Now remember, what we said is the power gets reduced by 1, right? And it's kind of like that x vanishes on over here, and d over dx just becomes 1. Everybody see that? So we just have 2x. Plus, and then what would you say is the derivative of y squared? 2y, right? Okay, and you said that it reduced by 1, so that y just kind of vanished on over there. So you get dy over dx. And dy over dx is the same thing as y prime. And then we have the derivative of 36. What's the derivative of a constant? 0. And so 0 times d over dx will give you 0. So the rule for today is this. When you take derivatives, anytime you take derivative of something with y, simply attach a y prime. So I've tried to explain why it happens. Some of you will remember that, some of you won't. That's okay. Just if you ever take a derivative with a y, attach a y prime. We good? So now let's solve it. We have 2x plus 2y y prime is equal to 0. And I want to solve for y prime. So I subtract the 2x. So 2y y prime is equal to negative 2x. I divide by 2y. I get y prime is equal to negative x over y. Everybody okay with that? Beige? Let's try to understand what the heck that means in context of the graph. So you don't have to write this down, but if you'd like to, you sure can. Can somebody tell me what that coordinate is for this graph? Close. What's the radius? Negative 6, 0. And this coordinate? 6, 0. This one? And this one? 0, 6, right? Okay, so if I draw a line that is tangent right here, somebody tell me what is the slope of that tangent line? Undefined. We say that a vertical line has undefined slope. Everybody agree? Well, watch if we type in the point 6, 0 into our derivative. We get negative 6 divided by 0. What happens if you divide by 0? See that? This tells us you don't just plug in the x value in this situation, you have to plug in the x and the y value. Okay? Somebody describe for me the slope right here. 0. So if I plug in 0 for x and 6 for y, I get negative 0 divided by 6, which is, see how it works out? Works out quite nice. In fact, watch this. Does everybody agree that in this quadrant right here, you have negative x and negative y? Describe for me the slope anywhere in this region right here. The slope would always be negative. Everybody agree? So if you plug in a negative for x, you get negative, negative. Whoop. Not necessarily negative 1. My bad. Negative, negative. And then we say that the y value is also negative, and that will produce a negative. So this does, in fact, produce the slope in any of those situations on the graph. Let's try some algebraic examples and skip the summary. It says use implicit differentiation to find the derivatives of the following equations. What is the derivative of 3x squared? 6x. Minus, what is the derivative of 4y? 4y prime. Good. Every time you see a y, you attach a y prime. Excellent. Is equal to? 4. Now what? Solve for y. So we have subtract the 6x, and we get negative 4y prime is equal to 4 minus 6x. Divide by negative 4. Y prime is negative 1 plus 3 halves x. Good? Yes. You could. But you can't in this situation, can you? So Jenna is 100% correct that in this situation, you could check your answer by solving for y. You may write this as an explicit equation in terms of y and come up with the same thing. But there's many situations where that doesn't work. What's different about this one? You have multiple y's. I'll show you what to do in that scenario. What's the derivative of y to the third?
3y.
3y squared times y prime. minus 5 plus 2y prime is equal to 3. So when you end up with multiple y primes, gather all your y primes to one side and everything else to the other side. So you can see here we get 3y squared y prime plus 2y prime is equal to 8. Anybody see what I could do to isolate the y prime? Factor it out. So I get y prime times what's left? 3y squared plus 2 is equal to 8. Divide. What do you think? You try letter C on your own. Go. When you're done, you can look up and glance. Getting a couple nods. So this is a small piece we covered a little bit last year, just to make sure you guys see this. If I came up with 1 minus 9x squared, and on the bottom I had 16y cubed minus 4y, are those the same? Yeah, so in this situation, these are the same because the top and the bottom are different by a factor of -1. And so if you factor in -1 on the top and bottom, the negative would cancel, giving what you have here. So as long as the top and bottom are switched by a factor of -1, you're fine. Now, why would that happen? I put my y primes on the left side. If you put them on the right side, you would have gotten this expression. They are the same. Okay, good work. What's different about letter D? What? What do we do? What do you do if you have 3x times y? Product rule. All right. Notice how it says f times g. I'm going to say that f is 3x, and I'm going to count g as just y. So product rule, what's the derivative of f? 3 times g, which is y, plus 3x times, what's the derivative of y? 1 y prime. So y prime. Derivative of 9x? 9. Derivative of 5y squared. Cool. Do you want to put your y primes on the left side or the right side? The what? The right side. Okay. So we have 3y plus 9 is equal to 10y y prime minus 3x y prime. Now what? Factor out the y prime. So 3y plus 9 is equal to y prime times 10y minus 3x. Divide by? Yeah, so 3y plus 9 divided by 10x. Well, it should be 10x, should be 10y, right? Sorry, 10y minus 3x is equal to y prime. Good. So we'll do E and F. We will not do these two. We'll leave those two for tomorrow, and you'll get a fair amount of time in class tomorrow to work on your assignment, okay? But let's finish off these two, okay? You guys are on a roll, and you're doing good. You're getting this. Okay, somebody letter E. The left side, super easy. Derivative of x, 1 equals. How will I find the derivative of sine of xy? Sine of xy. Chain rule. Yay, look at that. Love it. So what's the outside? Sine of u. What's the derivative of sine of u? Cosine of u. Look how good you guys are at taking derivatives. You rock. How will I take the derivative of x times y? Product rule, right? X times y. So this is F. That's G. Derivative of x times G is y plus x times y prime. So now I multiply those two together, right? So let's be careful with this as we use our parentheses. All right, 1 is equal to y plus xy prime times the cosine of xy. I want to get at the y prime. I have two options. I could either distribute the cosine through, or I could divide the cosine off. Which would you rather do? Let's divide the cosine off. What's 1 divided by cosine? Secant. Oh, look at that. Secant of xy is equal to y plus xy prime. So I divided by cosine, and 1 over cosine is secant. Yes?
Did you move the cosine to the other side of the cosine?
So I went like this, divide this by cosine of xy, which got rid of that, and then cosine of xy. 1 over cosine of xy is secant of xy. All right, so now what am I going to do to solve? Subtract the y and divide by x. So you get secant of xy, we subtracted the y, and then we divided by the remaining x, and that's equal to y prime. That's kind of nifty. I mean, think about that when we started today. No clue. Impossible. All right, last one. Letter F. Derivative of 4x. 4. That was easy. What do you think we do to find the derivative of x times tangent of y? Product. Derivative of x, 1 times tangent of y, plus x times, what's the derivative of tangent of y? Secant squared of y times y prime. Always make sure when you take the derivative of something that has a y, you attach a y prime. What are we trying to solve for? How will we solve for y prime? We will subtract tangent. So 4 minus tangent of y. It's like tanny. Is equal to x secant squared of y, y prime. Now I divide off yeah. And I'm just, there's a couple different ways you could write this, but I think that this is probably the most common way we would see this expressed. Y prime is equal to 4 minus the tangent of y divided by x secant squared of y. Good. Nice work. Good job. You guys are there. That's like your last derivative rule. we have applications of derivatives and all sorts of things, and we get to things called antiderivatives. That doesn't refer to somebody who's afraid of a derivative. It's something else. You didn't like my joke? That's all right. I may not be funny, but at least I'm funny looking. All right.